But to make my talk self-contained, I will also briefly review this classification again. This will be the basis of my argument. Then I will introduce the higher form symmetry analog of type A and type B Nambu-Goldstone modes. I will also argue that there are Nambu-Goldstone modes that are neither type A nor type B. And in fact, a class of instabilities can be understood as variant of Nambu-Goldstone modes that do not have usual linear or quadratic dispersion relations. And we can understand this using the higher form symmetries. Finally, I will discuss class of turbulence after this class of instabilities, and they seem to have some universal features, such as the generation of certain linking numbers and a self-similar inverse cascade. And this talk is mainly based on my recent work, two of which are in collaboration with Ryo Yokokura in Keio University, and one of which is a work in progress with Yuji Hirono, Kohei Kamada, and Ryo Yokokura. Okay, as we know, the notion of spontaneous symmetry breaking and Nambu-Goldstone modes are ubiquitous, and they have powerful physical consequences at low energy. For example, in solids, spatial translation symmetry is spontaneously broken, leading to phonons. In ferromagnets, spin rotation is spontaneously broken, leading to magnons. In superfluids, superfluid phonons associated with even particle number symmetry important in the hydrodynamic behavior at low energy. In nuclear physics, pions were initially introduced by Hideki Yukawa to explain the binding of nucleons, such as protons and neutrons. And pions can be understood as approximate Nambu-Goldstone modes associated with the chiral symmetry breaking in the underlying theory of the strong interaction, that is QCD. But the original formulation of the Nambu-Goldstone theorem assumes the Lorentz invariance. And in that case, the dispersion relation is always linear, and the number of Nambu-Goldstone modes is always equal to the number of broken symmetry generators. But there are examples, classical examples, such as ferromagnets, where the dispersion is quadratic and the number of Nambu-Goldstone modes is not equal to the number of broken symmetry generators. And the key to understand this abnormal dispersion and abnormal number of Nambu-Goldstone modes is the commutator of broken symmetry generators. And we can classify the Nambu-Goldstone modes into the so-called type A and type B. When a broken symmetry generator commutes with all the other broken symmetry generators, it is type A, and they have a linear dispersion. And on the other hand, if different broken symmetry generators expectation value of the commutation is non-vanishing, then they are type B, and they typically have a quadratic dispersion. For magnons in ferromagnets, where the spin direction is, say, aligned along the z direction, then the expectation value of Sz, which is equal to the expectation value of the commutator of Sx and Sy, is non-vanishing. So this is the example of type B Nambu-Goldstone mode, and one can find that the dispersion relation is quadratic. On the other hand, for magnon in antiferromagnet, the expectation value of the commutator of the broken symmetry generator is 0, and they have a linear dispersion. So this is an example of type A Nambu-Goldstone modes. And the counting of Nambu-Goldstone modes, type A or type B, were first conjectured by Thomas Brauner and Haruki Watanabe, and later proven by Yoshimasa Hidaka and by Haruki and Hitoshi Murayama independently, and 3 of them are in the audience. And I repeat the argument. And we can first construct the generic effective Lagrangian up to second order in derivatives without Lorentz invariance. Because of the absence of Lorentz invariance, we can have this, this term, which is first order in time derivative. And here, pi a is a field corresponding to some broken symmetry generator. And this first term means that pi a and pi b are canonically conjugate, so they represent one physical degree of freedom. Therefore, the number, so this is a case of type B. So the number of type B Nambu-Goldstone mode is given by the half of rank of this matrix row. Okay. At low energy, we can ignore this second term, which has two-time derivative. So at low energy, we can ignore this compared with the first term. Then this first term gives omega, and this two special derivatives gives k squared. That's why we have a quadratic dispersion relation. By using Noether theorem for this effective Lagrangian, the conserved charge corresponding to the field pi a is given by this expression. And by further using a canonical commutation relation for the field pi a, this matrix rho AB is proportional to the commutator of two broken symmetry generators. That's why the number of type B Nambu-Goldstone mode is characterized by the non-vanishing of this expectation value of the commutator of the broken symmetry generator. On the other hand, for type A Nambu-Goldstone modes, they represent one physical degrees of freedom, so their number is just given by the number of broken symmetry generators minus rank of this matrix row. And this is, so far, this is the story about the usual symmetry called zero-form symmetries. And we can extend the notion of symmetries to the so-called higher form symmetries. And here, I will focus on the one-form symmetry, which is a symmetry for a one-dimensional object like strings. The Wilson loop is one such example. The Wilson loop is defined as the loop integral of the gauge field A. Okay, and this Wilson loop is charged under the following one-form symmetry, namely A mu is assisted by lambda. Here, lambda is a flat connection. Although Wilson loop is a gauge invariant quantity, Wilson loop is not invariant under this one-form symmetry. So in that sense, Wilson loop is charged under one-form symmetry. So free Maxwell theory in the absence of charge and current have this symmetry. So we can derive the conservation law associated with this one-form symmetry. And the conservation law is given here. The divergence of J mu nu with two indices is vanishing. Here, J mu nu is just a field strength F mu nu. We can also construct a conserved charge or symmetry generator by integrating this conserved current over the direction perpendicular to this mu nu directions, which is nothing but the integral, surface integral of the electric field. So physically, this conservation means that in the absence of charge, electric flux is conserved. So this is a one-form symmetry. And in fact, this one-form symmetry is spontaneously broken in the vacuum in three spatial dimensions. And the order parameter is the Wilson loop, because Wilson loop is charged under this one-form symmetry. And unlike the usual symmetries, this Wilson loop is an extended non-local object. So in the terminology of Masaki's colloquium yesterday, this will be the generalized Landau paradigm. So if we take the loop to be rectangular, the Wilson loop is related to the potential between a particle and antiparticle. And in 3 spatial dimensions, Coulomb potential is proportional to 1 over R. So this Wilson loop is shown to be non-vanishing. Therefore, this one from symmetry is spontaneously broken. The massless photons in the vacuum can be understood as Nambu-Goldstone modes associated with this spontaneous breaking of one-form symmetry. Because in the vacuum, we have Lorentz symmetry, Nambu-Goldstone modes can have only linear dispersion relation, and they are type A Nambu-Goldstone modes. And we can ask whether there is a counterpart of type B Nambu-Goldstone modes, also for photons or for higher form symmetries. And the answer is yes. And here is an example. The example is the action electrodynamics in external magnetic field. Okay, here is the Lagrangian. Theta is the action field. F is the decay constant. F is the kinetic. F is the field strength. And we have a topological interaction between action and the photon. C is the anomaly coefficient 1 over 4 pi squared, which will appear frequently in this talk. And this theta action field is not necessarily the QCD action or action-like particle. And for example, the Lagrangian for the charge-neutral pion coupled to the electromagnetism is also described by this type of Lagrangian. In that case, pi FF tilde term describes the decay of charge-neutral pion into 2 photons. And this interaction was very important for the discovery of the chiral anomaly historically by Adler Berjakif in 1960s. And also, people consider the possible realization of this kind of Lagrangian in condensed matter systems with emergent action fields. So let us consider this Lagrangian in the external magnetic field, and then equation of motion for the action field and the photon are given like this. Okay. The important point here is that the action field and the photon are mixed with each other at the level of linearized equation motion due to the topological interaction in the presence of the magnetic field. So one of the field strengths is replaced by the external or background magnetic field. So they can couple to each other even at the linear level in the equation motion. Now, we can write down this equation motion in momentum space in this way. Here, let us consider the photon in the direction perpendicular to the magnetic field. And we assume the magnetic field is homogeneous in the z direction. Then here is the momentum expression in the momentum space, where the off-diagonal components originate from the mixing due to the topological interaction in the external magnetic field. And by diagonalization of this, we get these 2 modes. One has the quadratic dispersion relation, and the other is gapped. So this is similar to the situation for the type B Nambu-Goldstone modes for zero-form symmetries. And in fact, one can show that this mode is a type B Nambu-Goldstone mode related to the one-form symmetry.
Can you hear me? Yeah. So just to be sure I understand this, so the fields you vary with respect to is theta and an A field?
You mean
in the Lagrangian, just to understand. So what are the fields you vary with respect to?
Yeah, theta and
and A?
Yeah, gauge field. Yeah.
And the thing on the right, is this enforced as an external constraint after the variation, or?
External, which you mean this one?
Yeah. What does this mean? Does this mean I should plug it in at the start and then vary?
So we are considering the dynamical photons in the presence of the background magnetic field.
Okay. Yeah, but does this mean you enforce it after the variation as a constraint?
We have both dynamical and background fields. Okay.
Okay. Thank you.
something very elementary. It's C over 2 E dot B, right? F of dual is E dot B.
C over 2.
No, no,
This one.
yeah, isn't that the same thing as E dot B?
E dot B, yeah. And then
And
B
so
is,
if I take B to be B external, it's then E. But
E,
then it looks like it's E, but you have
Yeah, yeah,
omega there. So I think you mean A in that column vector. It's not EZ, but A,
A.
you know, gauge potential.
Why?
Because, well, because in that matrix, you have omega
Uh-huh.
times EZ in the off-diagonal term.
Yes.
Is it not omega times A? Not.
No. So
Where does the omega come? Alpha omega, where does that come from?
so omega, for example, we have a first order derivative here, and also we have a first order derivative here.
Oh.
Okay, I
Okay,
can
maybe we
explain
can
this
get-
way. So
Okay,
yeah, it's
maybe
easier
I'm wrong.
to take a specific gauge, namely A0 equals 0 gauge. Okay, although it relies on particular gauge. In that case, this topological interaction in the presence of the magnetic field can be written in this way. Okay. Then in this term, we have a first order time derivative acting on the gauge field. And you see this looks similar to the situation for the effective Lagrangian for type B Nambu-Goldstone mode for the zero form symmetry. That's why we have omega. Okay. Also, this argument relies on the particular gauge. We can also make an argument which doesn't rely on the particular gauge, namely, one can show that the expectation value of commutator for the broken symmetry generators involving one form symmetry is non-vanishing. Although I will not go into details. The details are given in this paper. And so this example of the action coupled to the electromagnetism in the magnetic field provides a example of type B Nambu-Goldstone mode for one form symmetry. For example, one can consider mixing of charge neutral fermion and photons in massless QCD in the presence of the external magnetic field. Okay. There are also other examples, which were discussed in other papers here. Yes.
It seems to me that in the two dispersion relations, which corresponds which? The first one is for.
First one is.
I mean
guess,
that which is proportional to the k square. Is dispersion for photon?
Yeah. First one corresponds to this one, and I think this one corresponds.
Then it means that the dispersion depends on the alpha, which means that some called the speed of it can exceed the speed of light.
Why?
If the, for example, alpha is larger than 1, then it means that.
Which speed are you talking about? So the dispersion is here.
Dispersion, from the dispersion, we can read out some speed of the particles. It means that if the alpha is larger than 1, which means that that speed of the particle is larger than the speed of light. Is it possible? If you take the, for example, strong enough
I'm not sure because
field.
I'm not sure if we can take alpha is equal to. Yeah, by the way, alpha has a dimension, so mass dimension.
So okay.
So
it does not
be
pay
by alpha.
dependent.
Yeah.
So anyway, in addition to that, even in the absence of this B field, so because of this parity violating term of the action and FF tilde, there is some kind of a variation of the dispersion on the polarization of the particle.
Yes.
So it seems to me that there is no such kind of terms in this setup. Then it means that you should just ignore that part.
Yeah, but we need some external background because this is a cubic term in terms of the field. So in order to affect the dispersion relation, we need a background magnetic field or background electric field or some non-trivial configuration of theta.
So okay, maybe we can discuss it later.
Okay, so yeah, but yeah, I want to focus on other variant of Nambu-Goldstone modes in this talk, which do not have the usual linear or quadratic dispersion relation. One example is photons at finite chemical potential mu5. Here mu r and mu r are chemical potential for right and left-handed fermions. And it is known that at finite mu5, we have a current proportional to the magnetic field. This is called the chiral magnetic effect. And here again, she is the anomaly coefficient. By inserting this expression into the Maxwell equation and eliminating the electric field, we obtain the closed equation for the magnetic field. Because of the additional contribution due to the chiral magnetic effect, we have this additional term in the equation of motion for V. And from this equation of motion, we can find the dispersion relation of photons. And dispersion relation depends on the helicity of photons. Depending on the helicity, the sign takes minus or plus. The reason why dispersion relation depends on helicity is because mu5 breaks parity. So the dispersion relation is not symmetric with respect to the parity. And for omega minus, we can find that this k squared minus k linear term becomes negative for some range of k, a small k. This means that omega minus has a positive imaginary part. So we have instability. The propagation of the photon grows exponentially. Okay. So this is called chiral plasma instability, or CPI for short, in medium, because it can be viewed as a parity odd generalization of the usual plasma instability. In the usual plasma instability, like Weber plasma instability, the unstable modes can be found by looking at the dispersion relation by solving the kinetic equation. And for the usual parity invariant systems, we can have unstable modes only when the distribution function of charged particles in momentum space is anisotropic. But in this chiral plasma instability, we can have unstable modes even though the distribution function is isotropic when we have a chirality imbalance. That's why this instability may be regarded as an extension of the usual plasma instability. In this reaction, it's not dynamical. They're just background field.
And then can you imagine some kind of like experiment, like optical experiment to detect this effect?
Optical experiment, I'm not sure which situation you are talking about.
Like unstable photons. So how can this like?
Yeah, if you can realize this, paramagnetic effect, say in wire metals, then there may be a possibility that we have this kind of instability.
So you're treating mu5 as an equilibrium parameter, right?
Mu5.
Yes.
Mu5, so mu5 is actually, mu5 exists only in no equilibrium setup.
Exactly. That's my point. So in equilibrium there is no chiral magnetic effect.
Right.
Therefore, if you're treating mu5 as a constant there, as a parameter, the picture is completely different. So so you are not going to see that in a Weissman metal ever, because mu5 is a dynamical quantity that you really have to.
Yeah. So mu5 is a dynamic. Yeah, mu5 should be treated as a dynamical variable, but I will talk about that later.
Okay.
Here, we just assume constant mu5. Yeah, eventually, in order to understand the evolution of the system, we need to understand the evolution of mu5 as well. Okay. So here's a schematic picture of the chiral plasma instability. So suppose we have initially homogeneous mu5, and let us consider the perturbation of the magnetic field, infinitesimally small magnetic field, and this magnetic field generates electric current by the chiral magnetic effect. And this electric current generates a magnetic field in this direction by Ampere's law. And now by the chiral magnetic effect, once again, this magnetic effect generates electric current in this direction. And further, again, this electric current generates a magnetic field in this direction. This means that the original infinitesimally small magnetic field provides a positive feedback to itself, meaning that we have instability. The magnetic field grows exponentially. And also, as you can see, the magnetic field configuration has a linking. And this linking is captured by the quantity called magnetic helicity, defined in this form. So the magnetic helicity is given by the volume integral of A dot B, where A is the vector potential and B is the magnetic field. And one can show that this magnetic helicity is proportional to the Gauss linking number, where C1 and C2 are closed loops along the magnetic fluxes. And the technical remark is that this magnetic helicity is not invariant under the large gauge transformation, but one can make it gauge invariant as explained by the previous speaker using the notion of non-invertible symmetry and using the TQFT. But I will not going to talk about this subject. Now one can ask the fate of this instability. Okay, I will discuss the evolution of this chiral plasma instability quantitatively later. But what happens qualitatively is that if we have an instability of the magnetic field in this direction, then by the Faraday's law, the electric field is also induced in the opposite direction to the magnetic field. Then the chiral anomaly relation, which relates chiral charge to the electromagnetic fields, tells us that the negative E dot B here decreases this chiral charge. Namely, as a consequence of this chiral plasma instability, the initial mu5 tends to decrease. That's why this plasma instability will eventually be saturated by the nonlinear effect of the chiral anomaly. In other words, this chiral plasma instability converts the initial chiral charge into the magnetic helicity. And phenomenologically, this chiral plasma instability was considered as a possible mechanism for the primordial magnetic field in the early universe and strong and stable magnetic field of magnetars. Now, I would like to argue that this chiral instability can be understood as a variant of Nambu-Goldstone modes. If we have a full Lorentz invariance, then the dispersion relation is always linear. Omega squared is equal to k squared. But in the presence of background fields, the Lorentz symmetry is explicitly broken. So in the situation for type B Nambu-Goldstone mode, as we have seen previously, we have a first order time derivative term. So we have a omega correction in the dispersion. This gives the type B dispersion relation. But there is another possibility that we have a correction for the first order in K in the dispersion. In this case, we have unstable modes. And this argument suggests that the presence or absence of unstable Nambu-Goldstone modes can also be judged by the symmetry algebra, similar to the type B Nambu-Goldstone modes. Okay? We can count the number of unstable Nambu-Goldstone modes by symmetry algebra. But here we are also interested in photons, so we need to generically use higher form symmetries. And we also need to change between omega and k. So the roles of temporal direction and spatial direction has to be also interchanged. That's the idea. because the general situation is mathematically involved. Here, I want to discuss the chiral instability as an example. Okay, thank you. So here is a Lagrangian. So we have a kinetic term, and we have an action, background action coupled to FF tilde. And we assume this theta is time dependent, and theta dot is given by mu5. And this Lagrangian actually describes the electromagnetism with the chiral magnetic effect. If we can write down the equation motion, then because of this term, we have additional contribution. We have additional current proportional to the magnetic field, which can be regarded as the chiral magnetic effect if we identify this theta dot is mu5. Okay? So this includes the effect of chiral magnetic effect. And we can see the dispersion relation using this Lagrangian. The simple way is to specify some gauge as equal to 0. Then by performing the integration by parts, this time derivative acting on the gauge field can be made to act on this theta, giving mu5. Then we have first order in spatial derivative. And that's why we have a k-linear term in the dispersion relation. Okay. Even without specifying the gauge, we can also argue the presence of the unstable mode by using the higher form symmetries. We can first construct the conserved currents from this effective Lagrangian as follows. And then if we are interested in the photons in x direction, we can take the symmetry generators as follows. One is the xy component of this J mu nu integrated over the perpendicular subspace. And the other is xz component of this J mu nu integrated over the perpendicular ty direction. Then one can show that the commutator of this broken symmetry generator is non-vanishing when theta dot is finite. In this way, we can understand the presence of unstable energy mode from symmetry algebra involving one-form symmetry. And more generically, one can show the following counting formula. The number of unstable Nambu-Goldstone modes in some spatial direction, XL direction, is given by half of rank of this matrix, which is determined by the symmetry generator in Li direction and symmetry generator in Lj direction integrated over the perpendicular direction. In the usual situation for the zero-form symmetry, we consider the symmetry generator at a fixed time integrated over volume. But in this case, we consider the symmetry generator in this direction or in that direction. And this symmetry generators are also extended in the temporal direction. Okay? And for the usual case, we also consider the equal time commutation relation, but in this case, we consider the commutation of two symmetry generators in the direction perpendicular to some spatial direction. Okay? That is a difference. And one can also derive a more general formula, not limited to the chiral instability for p-form fields, but yeah, the details are given in our paper. And there are also other examples to which our counting formula is applicable. One is the action electrodynamics in the external electric field. And this example was considered by those people. And Asaki in the audience also considers a possible realization in condensed matter systems. I think they consider massive actions, but for simplicity here, we consider massless action. Theta is action, kinetic term. This is again the kinetic term for photon, and we have a topological interaction. So previously, when we discussed type B Nambu-Goldstone modes, for photons, we consider external magnetic field. But if we consider the external electric field, that gives the example of unstable Nambu-Goldstone mode. And here is the dispersion relation. And when the photons are propagating in the direction perpendicular to the external electric field, then we have this kind of contribution. So this K-linear term is a signal of the appearance of the unstable Nambu-Goldstone mode. So this photon, so this mixing of action and photon is unstable for small k. And this emergence of unstable Nambu-Goldstone mode depends on the direction. So when photons are propagating in the direction parallel to the external electric field, we don't have any unstable mode. But this direction dependence can be captured by the this direction dependence of the commutation relation. And this example on the chiral plasma instability as an example involving one-form symmetry, and one can ask whether there is also an example purely within the language of zero-form symmetries. And here is an example, 2 plus 1 dimensional Goldstone-Maxwell theory in the external electric field. So this is a Lagrangian. We have 2 Nambu-Goldstone modes, theta and phi. They are coupled to each other via this topological interaction. Again, by inserting external electric field, the dispersion is something like this. And we have unstable Nambu-Goldstone modes for zero-form symmetry. Okay, from the phenomenological point of view, we are interested in the instability in medium. So let us consider, for example, chiral Maxwell equation, which includes chiral effect and also chiral anomaly in medium. So in medium, we have not only chiral magnetic effect proportional to the magnetic field, but also the ohmic current proportional to the electric field. By eliminating this electric field, we obtain this equation motion for the magnetic field. But this second term can be negligible compared with this first term at a long time scale. And in this case, one can again find the existence of unstable modes. In order to track the evolution of this system as a nonlinear level, as already asked, we also need to treat mu5 or n5 as a dynamical variable. And it is described as a chiral anomaly. As I already argued by using schematic picture, this nonlinear effect eventually saturates the instability. By integrating over this anomaly relation, we get this relation. N5 is a chiral charge of fermions, and integration over A dot B is nothing but the magnetic helicity, which expresses the linking of the magnetic fluxes. Physically, this equation represents the total helicity conservation, namely the helicity of fermions and the helicity of magnetic fields. The summation is conserved. One can also couple this theory to fluid velocity v when momentum is conserved. In that case, the system is described by chiral magnetohydrodynamics or chiral MHD. So in order to study the nonlinear behavior of system, let us study the spectrum of the magnetic helicity in K space. Okay, so we define this GKT. So this governs the spectrum of the magnetic helicity as a function of time. And generally, this spectrum is also related to the initial condition of our equation motion. But one may expect that after sufficiently long time, eventually this spectrum approaches some universal attractor solution. So let us assume that there exists some scaling solution after sufficiently long time, given in this form, where alpha and beta are some scaling exponents. And this is a scaling hypothesis, which needs to be checked numerically. And here are numerical results after a long time. And by rescaling with the exponent alpha equal 1 and beta equal 1/2, then eventually the spectra approaches a universal curve. So this suggests the presence of the self-similar scaling solution after sufficiently long time. And we can also analytically understand why the scaling exponents are given by these values. First, we can solve the equation motion analytically, partially in this form. Here, G0k is a spectrum of the magnetic field at initial time, t equals 0. And sigma is the conductivity again. And the part related to mu5, we cannot solve the part related to mu5 because it is governed by the nonlinear equation. So this is just given by the integral. But at least in order to have this kind of scaling, if we match the expression between the two, then beta has to be 1/2, okay, from this expression. Also, one can expect that eventually, after the chiral plasma instability, chiral charge approaches 0, and then magnetic helicity saturates as some constant. Then, by substituting this scaling hypothesis into this expression, and we can find the dependence of time as follows. So this part is just a constant. If this magnetic helicity approaches a constant, then this T dependence should also be a constant, which means that alpha should be equal to beta. In this way, we can get this value alpha equal 1 and beta equal 1/2. And this scaling suggests that the typical length scale of the system, which is given by the inverse of k, is proportional to the t to the 1/2. So the typical length scale grows as a function of time. So this is called the inverse cascade. Okay, maybe, yeah. We can also numerically simulate the chiral magnetohydrodynamic turbulence by solving chiral MHD equation. And here is the result. We initially provide a random seed magnetic field. And here is the evolution, 3D visualization of the magnetic fluxes. And eventually, the size of the magnetic field grows as a function of time and is bounded by the box size. So this is the inverse cascade. And we can also see this inverse cascading feature in the energy spectra. So eventually, the energy of the magnetic field is dominantly contained in the IR at long distance. And we can also see the similar structure for the fluid velocity. Okay, let us finally consider the nonlinear evolution of the other example, that is action electrodynamics in the external electric field. To make numerical simulations simpler, we assume homogeneity in x2 and x3 direction, and we also ignore the spatial direction of S3. Okay, this assumption is dramatic, but we can still see the inverse, similar inverse cascade in this setup. The equation motion, some of the equation motion are given here, and we also introduce dissipative effect for the action field pi. And we initially take the homogeneous external electric field, and then we solve this equation motion in a box with a periodic boundary condition. From this second equation motion, we can introduce the conserved quantity in this way. We have two terms. One is related to the electric field, and the second term comes from the topological interaction. And geometrically, this second term has a meaning of linking number, similar to the magnetic helicity. Okay? So we can also define the G function. So this is a spectrum of this topological quantity. And here are the numerical results as a function of time. So they are plotted for various values of time. And they are, of course, all different. But after sufficiently long time, they approach a universal curve if we rescale appropriately with the same scaling exponents as in the case of the chiral plasma instability, namely alpha equal 1 and beta equal 1/2. Initially, if the time is close to the initial condition, then this curve is largely deviated from this universal curve. But after sufficiently long time, they eventually approach the universal curve. This again shows the self-similar inverse cascade due to the topological interaction. And it seems that this class of instabilities and turbulence seem to have these universal features. Okay, I think it's almost time, so let me stop here. Thank you very much.